X in our case is always going to be our halides. So group 7F, fluorine, chlorine, bromine, or iodine. So we've seen these halogens a little bit, not so much the sulfur or the oxygen. Now, when we have oxygen bind, alcohols, when oxygen start to bind, we can actually start to form what are called alcohols. And these are things you guys should know and love at this point. You've been using hand sanitizer pretty much nonstop for the past year, right? What makes hand sanitizer go? Alcohols, right? Many of you are too young, but alcohol also makes alcoholic beverages do their thing. And we'll talk about that a little bit later in the lecture. But anytime you see something with a hydroxyl group, OH, this is what we refer to as an alcohol. So anytime you see an OH, that can even be on a sugar, it becomes an alcohol. Now, we can also have oxygen binding to carbon, but it could take a slightly different structure. So in the case of an alcohol, we have something R, which would be our carbon here. And then we have OH signifying an alcohol. Now, if we take that oxygen and we sandwich it in between two R groups, again, R can be anything, just not a hydrogen in this case. We form what's called an ether. So the standard structure for an ether, ROR or ROR, however you want to say it. And we can look at some examples. So ethanol here, this is what's in alcoholic beverages. Makes you, I guess, makes you feel nice. And then we have something like diethyl ether. So you can see diethyl ether, ether meaning ROR, the diethyl being there's two ethyl groups. So slightly new things, but we sort of mentioned alcohols and ethers in our very first lecture about organic compounds. Really, friend? You want to be like this? Okay. When we have our halogens, we start to form alkyl halides, and we've touched on this a little bit in previous lectures. Alkyl halides, as I mentioned, are halogens. So again, that group 7F, the second to last column in the periodic table, those are our halogens. Now remember, group 7F only likes to bond once, right? It's like hydrogen, it only likes to bond once. So typically when we have an alkyl halide, it's R group, so it's going to be some form of carbon bound to our halide. And as you can see, the halide has 6 valence electrons shown as lone pairs, and then it has one it's sharing with the R group. An example of this would be chloroethane. So we have the chloro part being the chlorine and the ethane part being ethane, right? Because ethane is 2 carbons. Then our sulfur groups, they form typically what we call sulfur hydro groups. Typically, we see them as thiols, where it's R sulfur bound to a hydrogen, but there are other forms, as we'll see. An example of this would be ethanethiol, which is the thiol group here being the sulfur hydrogen, and the ethane being our friend ethane. There we go. And just as a note, we're covering these not because it's fun or anything like that. I don't think chemistry is all that fun to cover just for the sake of covering it, but they do have real world applications. So for those of you who like coffee, what gives coffee its aroma? It's a thiol group. So you can see the SH here, it's 2-mercapto methyl furan. I think I said that right. As you guys know, pronunciation of chemicals is not my forte. That gives coffee its nice aroma. So when you smell your cup of coffee, you think a thiol group. N-furane, which the trade name, i.e., like Advil sort of name, would be ethrane, which is what you use to put people to sleep, and it's an anesthetic, right? Helps people fall asleep before they get surgery. And then finally, we have Taxol, which, as you notice, is a monster. It's derived from redwoods. And as you can see, this is an alcohol, right? It's got a bunch of OHs spread over it. This drug is actually kind of interesting. It's primarily used to treat breast cancer, but it has been shown to be efficacious in treating other diseases out there. But again, we could pick out exactly what they are. Taxol because of the hydroxyl groups, right? And N-furane because of the fluorines, but also you notice we have an ether group here, right? ROR, and then we have our halide group over on the left. So real world applications of these molecules. So let's dive into alcohols first, and then we'll kind of go through the other ones. Alcohols are probably the most common thing you see in a biological context. They're really common as byproducts of metabolism. They're just really, really common in general. And there's whole classes of organisms that produce them and break them down. And you'll learn that if you ever take a really advanced like chemistry course. Not so much fun, but there's lots of things you can do with alcohols. Now, our alcohols are classified by the number of carbons bounded to the carbon that has the hydroxyl group or that OH group. So we can see in this case, we have one carbon bound to a second carbon, which is then bound to the hydroxyl group. So in this case, we have what's called a primary alcohol because this carbon that's bound to the hydroxyl group, which makes it an alcohol, is only bound to one other thing, right? So it's only bound to one carbon atom. So this is what we call a primary or first degree alcohol. So it's kind of mimicking what we saw previously with like 1 degree carbons and 2 degree carbons, right? How many things they're bound to. Now, in this case, we're thinking about how many carbons they're bound to. Now, we can look at a secondary and a tertiary alcohol, or second degree and third degree alcohol, whichever one you want to call them. And you can see our carbon that is bound to the hydroxyl group is bound to 2 carbons here, and it's bound to 3 carbons here. Exciting stuff, I know. But again, recognizing it's secondary, tertiary, or primary simply by noticing how many carbons it's physically bound to. And the carbon we're talking about is always the one bound to the hydroxyl group. Remember, the hydroxyl group makes it the alcohol. Now, an alcohol that contains an oxygen atom typically has a bent shape like water, taking a bond angle of 109 degrees. So I think we can use a very simple example, methanol. CH3OH. Methanol is a kind of a stinky alcohol. It's in a lot of hand sanitizers, but it's very, very toxic. So I'm sure you guys heard about those people that died from drinking hand sanitizer, right? They died because there's a lot of methanol in there, and methanol is super toxic, like super duper toxic. Anyways, but as you can see, the bond angle here from the oxygen, hydrogen, right? So that hydroxyl group bound to this carbon takes a 109 degree angle, very much like water does, right? Remember, water, H2O, always takes this exact same shape, right? That Mickey Mouse sort of shape. Now, these are going to be polar bonds, right? Oxygen is in group 6 on the periodic table. So it has a pretty high electronegativity. In fact, it has the second highest electronegativity in the entire periodic table, right? Fluorine having the highest, oxygen having the second highest. Inherently, when you have an alcohol, they're going to be polar bonds, right? Because the electronegativity of oxygen, i.e. its desire or its hunger for electrons, is simply higher than carbon or hydrogen. Thus, when we're thinking about these polar bonds, remember, the electrons are just simply spending more time with the oxygen than they are with the hydrogen or the carbon. And remember, that sense of a polar bond creates that partial positive and partial negative charge. With a partial negative charge on the oxygen, because the electrons are spending more time with the oxygen, and a partial positive charge on the hydrogen in the carbon, because the electrons are spending less time there. So this is the same thing that water has, right? Water has the same dipole, again, all because of the high electronegativity of oxygen. Remember, a net dipole is pulling in one direction, right? It's pulling this way and this way, right? So it's all pulling the same direction, as opposed to, you know, something that's not a net dipole, which is we would have, say, pulling this way or pulling this way. But remember, identifying when you have polar bonds, it's all about electronegativity. In oxygen, fluorine, and all the halides have very high electronegativity. In addition, alcohols also have a hydrogen atom bonded to that oxygen atom, as we've been seeing, and thus it's capable of intermolecular hydrogen bonding. So if we have 2 methanols come together, well, because there's a partial negative charge on the oxygen and a partial positive charge on the hydrogen, a hydrogen bond can form, right? Remember, these are kind of fleeting interactions, right? You can have, you know, essentially, they form this very, you know, minute interactions. It's relatively strong, but kind of weak. It's not like strong as a covalent bond. It's kind of this interaction between the two. As a note, because of it kind of behaving like water, right? It's got a similar shape to water. It has that dipole like water. It behaves a lot like water. So when you have this, it actually creates pretty strong intermolecular forces, i.e. forces in between 2 molecules. So let me ask you guys this question. Given this, do you think alcohols are soluble in water? What do you guys think? What's the goal for solubility? Like dissolves like. So based on that, what would you say? Gail says yes, yes, Elsa. Everyone says yes, thumbs up. Anyone thumbs down? Okay. Answer is yes, right? Right. If you think about any alcoholic beverage, right? The alcohol is not like separated from the water, right? That's in the liquid, right? It's mixed in, right? It's dissolved into the water. And again, it's all because of this ability to behave like water. It's not water, but it has similar properties to water. Now, our alcohols have a inherently higher boiling point and melting point than hydrocarbons of comparable size and shape. So we can just do an example here. We have butane, C4, all right, H12, if I did my math right. No, I didn't do my math right, H10, all right. Butane, melting point, minus 138 centigrade, boiling point, minus 5 degrees centigrade. And we can look at propanol. So similar, again, we're replacing this hydroxyl group with a carbon, but we have 3 carbons, similar size, not too different mass-wise. Melting point, minus 127, boiling point, 97. So not too big of a difference here on melting point, right? Minus 138, minus 127, that's only about 10 degrees, but there's a massive difference on that boiling point, right? This boils at negative temperatures. This requires basically the boiling point of water, right? And as I've mentioned, they are soluble in organic solvents. So not just something like water, they're also soluble in organic solvents. So low molecular weight, i.e. with 6 or less carbons, are definitely soluble in water, as I've mentioned. Larger ones, it's a little bit more difficult because they're just so large. There's lots of intermolecular forces at play. So they're typically not soluble in water. But again, as I said, smaller ones, definitely going to be soluble in water. So methanol, ethanol, butanol, propanol, heptanol, no, not heptanol, pentanol, there we go. Those are all going to be soluble in water. Whereas some of the larger ones, like as we'll see in the lab, you'll work with octanol, not soluble in water. In addition, they're also soluble in organic solvents. So if I had something, if I had gasoline, for example, right, that's a hydrocarbon, it's an organic solvent, it would also be dissolvable in, say, gasoline or petroleum or something like that. So how do we name these suckers, right? I think that's kind of a good, it's kind of a good summation of what we've been doing a lot of, right? Spent a lot of time naming things in class, and we got to still name alcohol. So let's give the IUPAC name of this alcohol, right? So it's got a lot of similar ideas to naming as we would see for just regular hydrocarbons, right? When we named hexane, right, or we named any alkene or alkyne, right? Same set of rules. So in this case, we have this carbon, and the same thing that we always do. We have to find the single longest chain, but the chain has to contain the C that is bound to the hydroxyl group. So that's an important part. So you'll remember when we did the double bond, right? We had to include the double bond in the longest chain or the triple bond in the longest chain. Same thing here. So in this case, we have to find the longest chain, which includes the hydroxyl group or the part that makes it an alcohol. So we have 1, 2, 3, 4, 5, 6, or we could go 1, 2, 3, 4, 5, 6. It would be the same thing. So in this case, we have a 6 carbon chain. Now, normally we would name that hexane, right? 6 carbons. If it's an alkane, it would be hexane. But when we identify the presence of a hydroxyl group, remember that alone makes it an alcohol. So what we do is very much like when we were naming double bonds or triple bonds. We drop the A and E, so leaving us with the hex and giving us all. So hexanol would be the starting answer here. So we have hexanol. So that's fun. Now the rest of it is actually identical to what we've been doing thus far, right? Well, what do we have to do from here? Well, we've included the all part, as in hexanol. We have this methyl group hanging out there. So we have to figure a way to include that as well. So like we did before, we have to number the chain. Now, you need to number this carbon chain to give the hydroxyl group the lower number. So very much like we had to give the double bond or the triple bond the lowest number, we got to do the same thing here. So one of the things that's nice about the IUPAC system is that, a lot of these rules are consistent across, right? I keep bringing up like, oh, we do the same things for the double and triple bond because again, they are nice and consistent, which is good for you guys and obviously good for me for teaching wise. So we number the chain, making sure to give the hydroxyl group the lowest number. Now, if we go right to left, we have 1, 2, 3. That's cool. 1, 2, 3, 4. So we have to go right to left in this case, giving this hydroxyl group the lowest number. So very much like we would do a double bond, right? If we had a double bond where it would be hexene, we have to number that double bond. I'm sorry, we have to number this hydroxyl group. So in this case, it's a carbon number 3. So we have 3 hexanol. Right? Very again, like any side group, right? If it was a methyl group or an ethyl group, right, or even a fluorine, right, it's just the same number, right? Just number them. But remember, you always have to give this alcohol the lowest number possible. And so in this case, we get 3-hexanol. Nothing different here than what we normally get. And we have to name and number the substituents, right? Those R groups coming off the main chain. So we got 1, 2, 3, 4, 5 methyl group at carbon number 5. All right, 1 carbon is methyl. The answer ultimately comes to be 5-methyl-3-hexanol. So what does this tell us? The OL tells us we have that alcohol. Hex, 6 carbon chain. The 3 tells me that the alcohol is at the 3 spot in this 6 carbon chain. Then we have 5-methyl. The methyl group is at the number 5 carbon. Now, if I gave you this name, you could draw this carbon the way it's drawn here, or you could flip it, right? You could put the 3 spot here and the 5 spot here, right? It would be identical, right? If I just mirror image this, it would be identical, just as a note. So nothing crazy new. But again, we just have to take into account the alcohol and simply substituting our, removing the E here and replacing it with an all. Hexanol versus hexene. Now, just as a note, we'll go over this in class. We'll do some problems, like more substantial problems next week together, just as a note. So let's move on to cyclic rings, so our cyclos. Now, when a hydroxyl group is present in a cyclic ring, the hydroxyl group is automatically on carbon number 1. Fun stuff. And the 1 is typically omitted from the name. Makes sense as well. We saw the same thing with like double bonds, right? We always put it at number 1. Then, as we always do with our rings, we number them, giving the next substituent the lowest number. Nothing new, right? So in this case, we have 1, 2, 3, 4, 5, 6 carbon. So it's a hexane. It's cyclic, so it's cyclohexane. But there's an alcohol group here, right? That OH. So we consider that carbon number 1, and we need to give this methyl group over here the lowest possible number. Now, if we went this way, it would be 5. If we went this way, it's 3. So we have to go this way. So we end up getting 3-methyl, cyclo, because again, it's a cyclic ring, hex, because there's 6 carbons, all, there's an alcohol group, or hydroxyl group, I should say, at the first carbon. Second one, 1, 2, 3, 4, 5, so it's pent, so it's cyclopentane, because there's a 5 carbon ring. We always put the hydroxyl group at the carbon number 1, and giving this second substituent here the lowest number possible, which again would require us to go clockwise here, not counterclockwise. So we end up getting, again, omitting where the hydroxyl group is, right? We don't need to say that's 1. You technically could write, 2-ethyl, 1-cyclopentanol, but it's kind of redundant because the assumption we make is that the hydroxyl group is always at the first carbon. but you could write it and be technically correct if you wanted. But in terms of, probably the easier way to write it, and probably an easier way to kind of keep it in your head. Though I guess it kind of depends. Maybe it's easier to write the one for you. Doesn't matter how you write it; they're the same thing. But again, we go back to the same rules that we were before. 1, 2, that gives us an ethyl group where it's at carbon number 2, 2-ethyl cyclopentanol. I know your minds are blown. Not really, but you get the idea. So there are some pretty common names that we see for alcohols out there. You'll see these just like at the store. And if we have some simple alcohols, we typically use common names to describe them. So basically what we're doing in these common names is we name all the carbon atoms, the molecule, as a single alkyl group, and then we add the word alcohol after, right, with the space in between. So in this case, we have this alcohol, right? We could name it, it technically would be propanol, right? But if we have 1, 2, 3, it's propyl group. We have the alcohol, we call it propyl alcohol. So this is like rubbing alcohol. Like you could go buy this at CVS, for instance, or Walgreens, and you would use this to clean out wounds and stuff like that. Propyl alcohol. It's pretty common. Other common ones we'll get to. I thought I had this slide here. Actually, the other common ones we'll get to are methanol, ethanol, and propanol. We'll get there in a second. Now, compounds that have 2 hydroxyl groups, so stepping up the difficulty here, not really, are what we call diols, and that should sound familiar. Well, why does it sound familiar? Well, got the OL, right? That tells us it's an alcohol, and then it's got di. And what does di always tell us? If I have dimethyl, I have 2 methyl groups. If I have triethyl, well, I have 3 ethyl groups. And the same thing here. Triols are things with 3 hydroxyl groups, which are not uncommon. So for instance, we can look at an example here. We have 2 carbon chains, so it has to be ethane, and you can see we have 2 hydroxyl groups here. So we start with ethane, but we know we have 2 hydroxyl groups, so it has to be diol, right? Because it tells me I have 2 hydroxyl groups, and I have to number exactly where they are. 1 is on carbon 1, and carbon 2 here. 1, 2, ethane diol. Conversely, if we have a cyclic ring, 1, 2, 3, 4, 5, it's a pentane ring. So it's cyclopentane. I notice there's 2 hydroxyl groups. So I have to drop the E and replace it with a diol, because again, di meaning 2 alcohol. Now, you'll notice here that I have 1, 2. Previously, I told you don't number the alcohol. It's always at the 1 spot. But in this case, we have 2 alcohols. So we don't know, we have to actually tell the reader exactly where they are. So in this case, I have 1, 2, cyclo, because of the ring, pent, because there's 5 carbons, diol, telling me there's 2, i.e. di, ols, 2 hydroxyl groups. Good. I never could tell. It's easier to tell people's facial expressions when you can see their mouth. People are more expressive with their mouth than they are with their eyes usually. But so that's our alcohols. Now there are some interesting alcohols out there that you see in your average everyday life. So I've talked about methanol. I told you it's very, very toxic. It gets oxidized in your liver, and if it gets oxidized in your liver like alcohol, like ethanol does, it produces a lot of nasty byproducts that are very toxic to your body. So methanol is bad, but in a scientific concept, methanol is a very, very, very useful solvent. It's heavily, heavily used in the field of chemistry, and it's heavily used in the field of what we call mass spectrometry, which is using lasers to identify compounds. It's a pretty cool field. But again, methanol is super useful, but still super toxic to you, which is why you shouldn't drink hand sanitizer, because sometimes methanol is present in hand sanitizers. Ethanol, well, this is the fun alcohol. This is what's in beer, wine. Little bits of it are in kombucha. Any alcohol you can think of that you drink, it has ethanol in it. Typically speaking, we get this alcohol naturally. I say that with quotations, but we're really just taking bacteria or yeast to produce it, right? So when you drink beer or wine, there's microbes that ferment sugars into alcohol. So, and then we have propanol. It's also called isopropyl alcohol, and this is rubbing alcohol. So commonly used to sterilize your wounds and things like that. So alcohols play a role in your everyday life. They also play roles in your metabolism as well. So sometimes metabolisms will accidentally produce some of these things. Now, some other ones, ethylene glycol. So if you drive a car, this is a component in antifreeze. It smells kind of sweet. It's kind of a viscousy liquid. This is antifreeze. It's very toxic. So if you wanted to like murder someone, you could feed them ethylene glycol. It's very sweet. They wouldn't really notice they were drinking it. Probably shouldn't have told you how to murder someone, but I figured I'd just make mention of it. Glycerol, really common. So glycerol is actually a component of your phospholipids in your cellular membranes, but it's used lots of things. It's used in lotions, liquid soaps, shaving creams. It's sweet tasting as well. It's not toxic at all, so it can be used as food. So these are our cool alcohols. They play a lot of roles in your average everyday life, whether or not you realize it. So alcohols are cool. We're going to take a quick detour to talk about a few types of carbohydrates, but we're going to come back later in the semester and visit carbohydrates more in depth. Now, carbohydrates, as many of you probably know, they're long chains of carbohydrates. They do contain alcohols, whether or not you noticed or not, and they are naturally occurring. So they're produced by you, they're produced by plants, they're everywhere, right? So you're thinking about how organisms string together simple sugars, glucose, how they string glucose together, right? Now, one of the really common carbohydrates out there is starch, and this is the main carbohydrate you see in plant tissue. So I'm sure you guys might have heard like, oh, potatoes are high in starch. Well, why are potatoes high in starch? Well, plants, when they photosynthesize, they actually store their photosynthetic products as starch. Now, starch is just a bunch of glucose linked together. So you can actually break apart starch to get glucose. So for those of you that took my intro bio class with me last semester, you'll remember the amylase lab. The amylase lab was looking at the breaking down of starch into glucose. Fun stuff. In addition, we can actually look at cellulose. It's a carbohydrate. It's an alcohol. Now, cellulose is the main component of wood. It's also the main component of your clothes. So if you're wearing something that's cotton, it's chock full of cellulose. It's actually the most, one of the most abundant compounds on the planet. Right? Remember, trees are one of the biggest pieces of biomass on the planet, and cellulose is a primary component of trees and plants. So cellulose is super common. That being said, when you eat cellulose, you actually can't physically metabolize it. If you're lucky, you might have a microbe or two in your gut that can break it down via fermentation, but they're not particularly common in your gut. They're really common in nature, but not really so in your gut. So when you eat a salad or something, or flax or anything, or maybe you eat wood for some reason, I don't know. People do weird things. You actually can't break that down. So just as a note. And we can look at starch, right? So this is the primary component of the way plants store their glucose. But you can see these skeletal structures, right? They have their carbons and they contain oxygens. So you notice there's an ether group right here as well. But you notice they're chock full of these hydroxyl groups, right? Which makes them an alcohol, right? But you can physically cleave these apart and you can get an individual molecule of glucose right here, just as a note. We can also look at cellulose. Again, bunch of hydrocarbons linked together. There's oxygens here, so these are ether groups. But again, chock full of hydroxyl groups. So cellulose, technically an alcohol by chemistry sense. Now, you'll notice it says OSE. And for those of you that remember from Bio 1, anything that's labeled OSE is typically speaking a sugar. So just as a note, like glucose ends in OSE, fructose, sucrose, those are sugars. So cellulose is technically a sugar, but it's also an alcohol. So fun naming things between chemists and biologists. Now, this wouldn't be chemistry if we didn't talk about reactions, and alcohols, very much like everything else on this planet, can react. Now, common thing we see in alcohols is what we call dehydration reactions, and its name tells you exactly what is happening. You guys know what dehydration is, right? You're thirsty, you might be dehydrated. Well, why is that? Because you lost water, right? Now remember, the opposite of dehydration is hydration, which is where you add water. Now, in alcohols, we typically see dehydration reactions when we treat them with a very strong acid. So my goodness, am I ever going to say this acid right the first time? Sulfuric acid, H2SO4, very strong acid. We could also do hydrochloric acid, HCl, but in this case, we're using sulfuric acid, got it that time. And we can treat an alcohol with sulfuric acid, and what we actually end up creating in this reaction is an alkene. So not an alkane, because there's a double bond here. And what we're doing is this acid is basically ripping off this hydrogen and this oxygen and forcing a double bond to form between these two carbons. And we're also producing a water molecule at the end. Now, you guys might remember from chemistry last semester, right? We had replacement reactions, the double replacement reaction and substitution reactions, all those stuff. Well, we have a new name. Dehydration in this case is what we call an elimination reaction. And why is it called an elimination reaction? Well, because parts of the starting material are actually physically lost and a double bond is formed in replace. So nothing is coming here, right? When this reaction is going on, this is a closed system. There's nothing coming in here to bond, right? It's not like we have fluorine coming in here, right? There's no fluorine here, right? So for these carbons to be happy, they have to form that double bond. So in this elimination reaction, we're eliminating this water down here, forming a water molecule, and then forming an alkene. I know, exciting stuff. I can see everyone's face. Everyone is very excited. So let's look at another couple of these reactions. So we can look at ethanol, where we have our hydrogen and our hydroxyl group here treated with sulfuric acid, producing ethylene in water. Ethylene is a commonly found in gaseous form. It makes plants ripen, or fruits ripen, just as a note. And then we have a cyclohexanol here, treated with sulfuric acid, producing cyclohexene, ene part being the double bond, as well as water. So that's what we're looking at here. Now, when alcohols are asymmetric, there can actually be two potential byproducts here. Now, what do I mean by asymmetric? Can anybody pick out what I mean by asymmetric here? Well, they're kind of the same. They're not all that different, right? You can look at these two compounds. All that's different is the double bonds here versus here at the end. But what do I mean by asymmetric here? What do you guys think? The two different ends. You're going to say? Well, yeah, they would be constitutional isomers, definitely at the end. It's a good point. I wasn't even going to say that, but good point. But yeah, Hilsa's right. If we think at the central carbon, right, it's bound to the hydroxyl group, right? It's a 2-degree carbon because it's bound to two distinct things. But on the left and the right, they're not symmetrical, right? On this side, there's a hydrogen, 3 hydrogens. This side, there's 2 hydrogens and a methyl group. So they're not symmetrical. And because of that, when you treat this with a strong acid, sulfuric acid, got it right that time, you can produce either 1 butene or 2 butene, because the double bond can actually go in either place. And you notice we take a different hydrogen each time. In this case, in one case, I could take this hydrogen, which would then let me form this molecule, or I take this hydrogen, which lets me form this molecule. So we have 2 potential products here, and it depends on which hydrogen we choose. That being said, as you can see at the bottom, there's Zatsev's rule, I believe. Again, pronunciation is not my forte, but basically what his rule says is that the major product always has the most alkyl groups bonded to the CC. Alkyl groups here. So whichever side has the most junk, basically, is what his rule says. If there's more stuff, basically, if there's more stuff over here versus here, it will be on this side. If there's more stuff here versus here, it'll be on this side. That's what Zatsev's rule says. And you can see, in this case, we're producing the major product is going to be 2-butene, which means that some of the time we also produce 1-butene. So in this reaction, we would actually have 2 distinct products, but the vast majority would be 2-butene, and a very small amount of it would be 1-butene. And again, both produce water. But again, I'm not going to ask you about this, but it bears mentioning that this is a thing. So. All right. So in addition to hydration, we can also have oxidation of our alcohols. So remember, oxidation is involving with the loss of electrons, right? And then its counterpart is reduction, which is something gains electrons, right? Now, when alcohol is oxidized, it leads to an increase of the number of carbon to oxygen bonds. And as you can imagine, if you increase these bonds, you're also decreasing the number of CH bonds. So let's oxidize this arbitrary alcohol. So we have CHOH. We oxidize it, which is just defined as O in brackets here. What ends up happening is that these 2 bonds are broken, and a new double bond between carbon and oxygen then is formed. Now, why is this oxidation? Can anybody pick out why this is oxidation? Why is it oxidation? Why is this reaction that we're seeing oxidation? What signifies that it's oxidation? Yeah, you're getting there. So it's all about those electrons, right? So we're losing electrons here, right? We're losing these, right? And we're stuffing them into here. So it's an oxidation reaction. Good. Now, the symbol we typically see is O. It's typically an oxidation reagent. In this class, we're commonly, very, very commonly going to see potassium, 2 potassium, chromium, 2, oxygen 7. That's the most common oxidant we're going to see. And in fact, we're actually going to use this in lab at some point during the semester. So this is what we're going to see. Typically seeing, if you see this, it means an oxidation reaction is going to happen. So now, let's bring back those primary, secondary, and tertiary carbons. What do they do differently from one another? Well, when we have a primary alcohol, or that first-degree alcohol, so remember, first-degree alcohol, it's only bound to one other carbon, signifying it's a first-degree alcohol. Now, our primary alcohols are oxidized first to aldehydes, which have the generic formula RCHO, or R2, kind of like R2, like R2D2. Was that too nerdy? Sorry. Because basically what you're doing is replacing one carbon hydrogen bond with a CO bond. So what this looks like, it's actually a 2-step process. So we have ethanol, S meaning 2 carbons, all meaning the alcohol group. It's oxidized again by that potassium chromate substance I have on this previous slide here. It produces acetyl aldehyde, again, because it's an aldehyde, RCHO, RCHO, aldehyde. Then aldehydes are then further oxidized to carboxylic acids, RCOOH, R2, replacing one CH bond with a CO bond. So we start off with acetaldehyde here. We oxidize it further, giving us COOH still bonded to that methyl group. Exciting stuff. So this is what's happening just with primary alcohols. What's happening with secondary alcohols? Well, secondary alcohols are oxidized first to ketones, which are R2CO. So in this case, we have some arbitrary second degree alcohol, C, and again, it's secondary because it has 2 carbon groups right here. Those R groups, in our case, will be carbons. And it's got the OH, so thus it's an alcohol. Now, what we're doing is replacing 1 carbon-hydrogen bond here with a CO bond. Well, what we end up getting is RCRO, which is the standard formula for a ketone. R2, meaning these 2 bonded to a C, which is then bonded to an O. So again, we're losing hydrogen here and hydrogen here, forming a double bond. So we're oxidizing this substance. Now we can see this in action with 2-propanol. It's propanol because it's 3 carbons. Indicating prop O, telling there's an all, and you can see that the hydroxyl group is at the 1-2 or 1-2 carbon spot. So it has to be 2-propanol. When this is oxidized, as you can see, we form acetone, which is, again, same structure, right? The R groups are going to be these 2 methyl groups. This carbon is this carbon, and this oxygen is this oxygen. So we have ketone. Ketone, acetone is a ketone. Now, who has heard of acetone? Everyone. And what's acetone? Yeah, it's nail polish remover. Right. So maybe you didn't know, but your acetone is a ketone, and it could be formed by taking propanol, oxidizing it with our monster chromium molecule, producing acetone. I think that's actually how they produce it. This is really easy to produce 2-propanol, and I think that's how they produce acetone, if I'm not mistaken. I could be wrong, but I think that's how they do it. And finally, tertiary alcohols. They have no hydrogen atoms bound to the carbon, so they actually don't get oxidized, which is nice. I mean, not have to remember anything else. So we have a tertiary carbon bounded to 3 R groups. Again, 3 different carbons here. No reaction will occur in the 3-degree or tertiary alcohol, which again is nice because it's less things to remember. In terms of like remember, I would say, as someone that's going to have to make your sim, this is going to be in terms of what to remember. You're going to want to remember, some things like this, generalized formulas. It won't be a huge part of your exam by any stretch of the imagination. Just to let you know. So let's talk about health. So what happens when you drink anything? Or what happens when you drink an alcoholic beverage? I mean, a lot of you are too young, so you should never have been, according to the government. But for those of you that are old enough, when you drink ethanol, or if you decide to drink hand sanitizer for some reason, ethanol is actually kind of an interesting compound. Now, it's toxic. So as you guys probably know, if you drink too much alcohol, you will die. But let's talk about why it is physically toxic. Now, when alcohol hits your liver, so that's one of the detoxifying organs of your body, right? Your liver's, kind of the big one, and then your kidneys are also the other, detoxifying organ. But once it hits your liver, the alcohol is taken apart essentially by an enzyme, which we call aldehyde dehydrogenase. And this basically acts as an oxidizing reagent. So it's replacing that potassium chromium molecule I showed you previously. So what ends up happening is you have ethanol. So again, you could drink a beer, wine, whatever. It's oxidized first to acetaldehyde, and then finally to acetic acid. Acetic acid, anybody recognize acetic acid? You guys used it in chemistry lab last semester with me. I hate acetic acid so much. It's found in ketchup. Vinegar. Yep, acetic acid is vinegar. So when you drink alcohol, it's actually oxidized fully to acetic acid, which is non-toxic. It's easily getting rid of by your body. Vinegar is easy to get rid of. However, when you drink too much and too fast, you actually have a buildup of acetaldehyde, this intermediate. Acetaldehyde is actually not super toxic, but it's relatively toxic, especially as it builds up. So if you drink, say, 10 shots in a row or something like that, you're going to start to build up a lot of acetaldehyde. And if you build up enough of it, it'll eventually be fatal to you. So if you ever wonder why alcohol is toxic and bad for you, it's because of this. Drinking it at a normal pace leads to this full reaction. Drinking it at an unnatural pace leads to just this truncated reaction, and your liver simply can't catch up, right? Chemistry can only happen so fast, right? Your body can only handle so much. That's fun. Methanol, as I've mentioned, is pretty toxic. Now, methanol, if it's consumed, is actually oxidized first to formaldehyde and then formic acid. Now, this is a fun one. I'm sure you guys have heard of formaldehyde before. What do we use formaldehyde for? Not in the lab, of course, but in society. I heard someone say preservative, but for what? Corpses. Yeah. So we use this to actually preserve corpses, right? So if you ever dissected stuff, it's commonly, well, not nowadays, but it used to be preserved in formaldehyde. It's a fantastic preservative. Why? Because it kills microbes. And why does it kill microbes? It's really toxic. So when you have a buildup of these, not the methanol directly acting on you, but when it breaks down either partially or fully into formic acid, these start to build up, and it leads to decreased blood pH, which is bad. So your blood pH should be consistently 7.3 to 7.4. When it goes higher than 7.7, you're in big trouble. It's called alkalosis. You can die relatively rapidly from it. It can also lead to blindness and eventually death if there's enough of it. Now, formaldehyde on its own is pretty toxic, but formaldehyde has to build up in meaningful concentrations to be toxic. So minute concentrations of formaldehyde, for instance, if you like accidentally got some in your mouth because you were in the lab and something splashed in your mouth, you'd be fine. You also can find decent amounts of formaldehyde in apples and other fruits. It's a really common byproduct of metabolism. You have it in your body all the time. But the key here is if you ingest a lot of it, it's bad for you. So little bits of formaldehyde, no problem. Your liver can handle that like that. Large amounts, not so good. Formic acid is an interesting acid. It's bad for you, as it says, but it's actually kind of an interesting compound. We're going to use this in lab later in the semester. Formic acid is actually produced pretty commonly in the insect world as defense. So ants produce formic acid, a lot of them, to ward off predators. So if you go to deep in the woods out in Western Mass, you can find ant hills where there'll be ants kind of hanging out on the hill. And if you go near them, they'll spray formic acid at you. I know that doesn't sound cool. I think it sounds awesome because I like ants. I like ants a lot. But that's what they spray at you. And actually, it's funny, interestingly enough, they use this reaction to make it. So just as a note. Anyways, that's my little tangent. Figured I'd inject some interesting stuff here. Now, alcohol in small amounts, as you guys know, causes all sorts of interesting things: dizziness, giddiness, decrease of social inhibitions, right? You guys know that stuff. Large amount causes really severe things. Even larger amounts can lead to really serious things, coma, death, like that. And again, it's all because of that reaction. Now, chronic excessive alcohol leads to cirrhosis of the liver, so hardening of the liver. So the buildup of those compounds leads to your liver becoming non-functional and hardening. So those people that have been alcoholics for years and years, their liver is hardened because this chemical reaction is happening over and over and over again. And just as a note, you guys probably heard this, but pregnant women shouldn't drink alcohol because ethanol actually physically can cross the placenta. Alcohol is readily just passed through the placenta and affects the little baby or the future human inside. And they simply don't have the enzymatic machinery to break it down yet. You need a fully formed baby to, a baby that's been given birth to break down alcohol. So, all right. So that's alcohol. Hope you learned something about alcohols, not just the crazy stuff I just told you, but the namings. Now, moving on, we have ethers. Now, ethers, as we mentioned, have two alkyl groups or two R groups bonded to an oxygen atom. ROR, ROR. That's how you know it's an ether. It's the two lone pairs on the oxygen as well. These R groups can be the same or different. So in this case, we have two ethyl groups here. In this case, we have an ethyl group and a methyl group. So two distinct groups. Now, oh, why does it always do this? Now, an ether has an oxygen atom with a bent shape, very much like water. So like we saw for the alcohols, that 109-degree angle here, in this case of dimethyl ether, has a bent 109-degree or 109.5 degrees angle. So water's angle. Again, all because of polarity, right? Carbon is less electronegative than oxygen, thus polar bonds. Now, ethers do some cool stuff. Now, ethers can actually be found in a ring, which I think looks pretty cool. So this is what we have, ether. So ROR, but in this case, it's a cyclic ring, right? It's a 3-member ring. I know it doesn't look like a ring, but ring, remember, means just it goes like this. Now, a ring that contains a heteroatom, so two of the same things. Right, in this case, we have 2 methyl groups, is called a heterocycle. And a 3-carbon heterocycle is called an epoxide. Epoxide. So, yeah. And so it's just some examples of these. So we have, I don't remember how to spell this one, disparler, I believe that is. So you can see it's that cyclic ring of 3 carbons. And I forget what this is off the top of my head. I'm sorry. I forget exactly what that is. But in this case, for our second example, we have hemibrevetoxin B. So you notice that it has ethers here, ether here, ether here, and ether here. Hemibrevetoxin is kind of cool. It's produced, as you can see from, well, maybe you can't see it in the back, but from front, this is a red tide. It's a toxin produced by dinoflagellates. It's pretty toxic. So when beaches get shut down on the Cape because there's red tide, you can blame one of the classes of hemibrevetoxins, which are all ethers, ROR. As we mentioned, ethers typically have, well, not typically, ethers have 2 polar CO bonds because the electronegativity difference between them. ROR, electronegativity here is higher than it is here and here. Thus, it creates that net dipole, as we saw with alcohols, right? That's why it gets that similar shape to alcohol, similar shape to water, because oxygen is just so much more electronegative than carbons. Now, remember, there's no hydrogens bound here. So if you saw this structure and there was a hydrogen there, it's not an ether anymore. There's simply no hydrogen in this case. And because of that, even though that has strong dipole interactions here, there's no intermolecular hydrogen bonds because there's no hydrogen, right? And remember, the hydrogen has to be here, not here, right? There's no difference in electronegativity here, so thus there's no dipole. The only dipoles that exist are here. So, what do we know about the properties of ether? Well, with what we just discussed, ethers have very strong intermolecular forces than alkanes, but very, very weak intermolecular forces, especially in relationship to alcohols. Remember, alcohols have very, very high intermolecular forces, i.e. between 2 distinct molecules, as opposed to intermolecular forces is within a single molecule. I have a typo there. It should be intra. Anyways, as a result, our ethers of comparable size and shape to an alkane or an alcohol have higher melting and boiling points than our hydrocarbons, so our alkanes, and lower melting and boiling points than our alcohols. And so you can see examples of this. So we have propanol having the highest boiling point, methyl ether. Well, that's not right. Ethyl methyl ether. Sorry, I don't know why that's not there. Has a boiling point 11 C, and then butane, which is just a straight hydrocarbon, has a boiling point of -5.5 degrees C. A lot of weird stuff going on with my slides today. I don't know why. So again, gives ethers kind of this in between. Alcohols having the strongest, highest boiling point, followed by ethers, then followed by straight up hydrocarbons. Now, ethers themselves are soluble in organic compounds. Now, lower molecular weight ethers, i.e. with 5 carbons or less, are soluble in water. So they can be dissolved in water. As in the case of these very small ones, water can actually hydrogen bond to the oxygen. So in this case, we have water here bound to dimethyl ether. We'll get into naming in a second, but you can see dimethyl ether, ROR. But you can see the structure here. The oxygen has a net dipole, right? It has a partial negative charge on it, because again, it's more electronegative than either of these carbons. So with that slight negative charge here, it can interact with the hydrogens here. So because of that, small ethers, 5 carbons or less, are soluble in water. So remember, like dissolves like is the general rule. If it has a property similar to water, it can dissolve in water up to a certain point. Now, higher molecular weight ones, so 6 carbons or more, are insoluble in water. So it's kind of like alcohols. Bigger alcohols simply just can't dissolve in water, just a size issue. Too much intermolecular forces going on. So simple ethers are typically assigned common names. And we saw this with alcohols as well. But we do name both of the alkyl groups, i.e. both of the R groups, so ROR, ROR, and we arrange them alphabetically. So in this case, and then finally we have to add the word ether to the end. So in this case, we have ethyl, methyl, ether. What does that tell us? Well, ether tells us it's ROR. Ethyl tells us there's an ethyl group. Methyl tells there's a methyl group. And because there's an ether, they have to be bonded to a central oxygen. Now, you could write, so technically, like if we read this, if I were to draw this, right, ethyl, methyl, ether, I'd want to put the ethyl group here, the oxygen here, and the methyl group here. These would just be identical compounds, just as a note. If you flip this over, right, it's an identical compound. Conversely, if we have ethyl, ethyl, it would simply be diethyl ether. So bringing back those di-tri rules that we discussed. Get away. Now, more complex ethers, so just beyond this very simple set that we discussed here, we use that IUPAC system. So that nice ordered system that I know you guys all love deep down. Now, one alkyl group is named as a hydrocarbon chain, and the other is named as part of a substituent bonded to that chain. So what does that mean? Well, in this case, we defined, if we have ROR, we have to take one of those groups, and it's named as a hydrocarbon, so meth. And the other is part of a substituent chain. So in this case, we start with methoxy because we have meth, ROR, bounded to the oxygen, bounded to something else. So methoxy. In this case, we have an ethyl group, S, because there's 2 carbons, O, then there's something over there, so S-oxy. So let's apply this to a much bigger system here. We have this big, long hydrocarbon, but you'll notice ROR. So there's an ether. So we have to use ether. So in this case, we have to identify the longest chain. That's you guys know that. We always have to identify the longest chain. However, the longer chain should be an alkane, and the shorter chain should be what we call an alkyl oxy group. Because again, it's all relative to this system here, ROR, ROR. So this side versus this side, right? So we have a two-sidedness to this, right? ROR. So what we're doing is saying, okay, the longer chain will be named as an alkane, and the smaller chain will be called an alkyl oxy group. So clearly, 1, 2 carbons, 8 carbons, 8 is bigger than 2. You guys know math. So we have to have the 8 carbon chain be called octane. So that's your first step. Identify where the ROR is, ROR. Which side of that oxygen has the longest chain? You define which has the longest chain, thus giving it its standard alkane name, in this case, octane. If it was 2 carbons, it would be ethane. right? Or 3 carbons to be propane, and so on and so forth. So that's the first step. Identify where the ROR is and define whichever chain on either side of it is the biggest. And that gets an alkane name. In this case, we have octane. Then we have to apply those other nomenclature names, right? Those rules that we know. So in this case, we have to define this group as something, right? This OCH2CH3. But it's coming off this larger octane chain. So we have to number it, right? And as we know with numbering, we got to give these puppies the lowest possible numbers. So in this case, we go 1, 2, 3, 4. It's shorter than going 1, 2, 3, 4, 5. So 2 distinct ways to number, but going from right to left here is the lowest. So 1, 2, 3, 4. So we start off with octane because we have this long chain of octane. Now we simply have to say, okay, where is our ether coming off of? In this case, it's carbon number 4, which is how we get the 4. And to defining an ether, we simply take how many carbons? So we have 1, 2, so that's an ethyl group. And all we do is substitute S, so it would be ethane, with S oxy. So you see we have oxy here. S as an ethane, oxy telling us there's an oxygen. So S oxy. I know it's kind of weird, but that's how you do it. S oxy. This was 3 carbons, it would be prop oxy. So 4 tells us it's on the 4th carbon. F oxy tells us there's an oxygen bound to an ethyl group here. S meaning 2 carbons. Octane telling us there is a 8 carbon chain. And again, substituting names that we know, right? We know S. Right? This is exactly the same IUPAC naming rules as before. We're just adding a new thing, right? So instead of ethene or ethine, it's ethoxy. So again, new, sounds funky, but same idea as what we've been naming previously. There was the double bond there. It would be ethene, right? Now it's just ethoxy, because why oxy? Our beloved friend oxygen is there. So it's an ethyl group bound to an oxygen. And when we know that's the case, if we see oxy, we know it has to be our friend in ether. How are we feeling about that? You get a chance to try it in your homework, so and we'll go over it more next week. Now, ethers have been used kind of a long time. So you see in 1846, our friend William Morton was actually using an ether diethyl ether. So it's one of those simple ethers, not this monster that we just named. Now, he was using it as an anesthetic. So just helping people relax and go to sleep, right? Good stuff. Now think about what dentists do. Dentists either drill your teeth or they rip it out. Now, for those of you that ever had a filling or a tooth removed, imagine how much that would hurt without Novocaine, right? That compound they inject into your jaw to numb yourself, right? Or pretend if you had surgery. Imagine how much it would hurt if you had surgery and they cut you open to operate on your bowel. Anesthetics, like diethyl ether, put you to sleep so that when someone rips your tooth out, when someone cuts you open, you're not awake for that. You're not experiencing that pain. There'll be pain after, obviously, but you're not experiencing the really hard pain of ripping your tooth out. That would hurt a lot, like a lot. So, anyways, that was 1846. Now, modern variations of this, we've talked about this one, enfurane. We also have isofurane, and we also have methoxyfurane. Again, you can see they're all ethers. Ether, ROR, ROR, ROR. They're all ethers. But it started with diethyl ether, and now modern anesthetics, again, helping you fall asleep so you don't feel the pain of surgeries or teeth pulling, which is a horrible experience. They are ethers. Good stuff. Toxic in high concentrations, but good stuff. All right, so our final topic, well, close to the final topic today is going to be alkyl halides. Now, as we discussed before, when you have an alkyl halide, halide refers to halogens. Group 7A, second to last column in the periodic table. These puppies have 7 valence electrons, which means they only bind once. So you see in this example back here, fluorine, chlorine, they're both halogens. They only bind once. Now we classify these ones by the number of carbon atoms that are bound to the carbon that has the halogen. So in this case, this is the carbon that has the halogen. Remember, halogens are always designated with X, with 6 valence electrons hanging out on the side as lone pairs. In this case, there's only one thing bound to this halogen. So it is a 1 degree or primary alkyl halide. Remember, alkyl always refers to the carbon, right? Alkyl as an alkene, right? Second degree should make sense at this point. Carbon that's bound to the halogen has 2 things attached to it. Again, we don't include hydrogens here. And the 3 degree or the tertiary has 3 carbons bound to it. Same with alcohols, right? Nothing new. Now, as with our alcohols, halogens are very, very electronegative, right? Electronegative, there we go. Fluorine is the most electronegative atom on the planet. So you can imagine, given that our alkyl halides contain very polar carbon to halogen bonds, right? These compounds have some of the highest electronegativities in the periodic table. Halogens, they're so close to filling that outer electron shell, they're super hungry for electrons. So they are very, very, very electronegative. So they are not capable of intermolecular hydrogen bonds because they only bond once. You'll never see a halogen bound to 2 things. You'll never see that. They only bind once, like hydrogen does. But as a result of that, they actually have very high melting points and boiling points than similar alkanes, but they still have lower boiling points than alcohols. Now, why is that? Remember, alcohols behave a lot like water, and water inherently has a very high boiling point. So you can see here, the C to C bond is polar, creating a net dipole towards the chlorine, in this case, where we have a partial positive charge on the carbon and a partial negative charge on the chlorine. No hydrogen bonding can happen here. Hydrogen bonding doesn't happen with halogens. They just don't like it. So. And as I mentioned, chloropropane being an alkyl halide has a slower boiling point. I'm sorry. I jumped the gun on this. But you'll notice that the size of the alkyl group, so whatever is attached to the halogen, as you increase the size of that, so we go from ethane to propane again, you'll notice that the boiling point increases. You also notice is that as we go from chlorine to bromine, so going a bigger halogen, so we're going down the periodic table in this case, so the molecules are getting bigger, that also increases the boiling point. I thought I had another one here to show you how it relates to just hydrocarbons and alcohols, but I guess I cut that slide. Anyways. So let's talk about how you name these suckers. And that will be sort of our last thing of the day because we're just about out of time. So let's give the IUPAC name of this monster here. So very much like we've been doing, find the parent carbon chain containing our halogen. Well, in this case, this is the parent carbon chain. It has to, remember, we want it to be the longest possible chain. 7 carbons tells us it's heptane. From there, we just have to apply all the normal rules of the IUPAC system. We number that chain, but in this case, we have to give the halogen the lowest possible number. So if we go right to left, the halogen gets 3. If we went left to right, the halogen would get 6. So we have to go right to left here. So we see that the halogen's at carbon number 2, and the methyl group is at carbon number 5. So when we have a chlorine, it becomes chloro. When we have a fluorine, it becomes fluoro. When it becomes a bromine, it becomes bromo. Iodine, which is my favorite, is iodo. Kind of breaks the rules because iodine is spelled kind of weird. But just as a note, you just kind of like drop like the back half of the halogen. So in this case, we have chlorine, which is chloro. It's at carbon 2. So 2 chloro, 5-methylheptane. And again, the rules of being in alphabetical order also matter here. Chloro is first, methyl is second. If we had bromo, again, it would also be first. So always alphabetical order. Now, just a couple cool things alkyl halides are known for. Chloromethane, CH3Cl, is actually produced by kelp, algae, and it also comes from volcanoes. Doesn't really do anything particularly cool, but it is a natural product. Dichloromethane. So you see we have dichloro because there's 2 chlorines here. The solvent, it actually used to be used to decaffeinate coffee. They don't use it anymore. It's too toxic, but they used to decaffeinate coffee with this back in the day, like, back in like World War II. Science was a lawless place back then. Just doesn't know. And then we can look at trichloromethane, CHCl3, which is also known as chloroform. I'm sure you guys have heard of chloroform. You see it in like spy movies where they have it in a rag and they put it on some guy's face and he falls asleep right away. Right, so you can use chloroform to do that. As a note, chloroform doesn't work that fast. You have to hold it on someone's face for like 5 minutes for it to work. So I apologize if I've ruined any spy movie or thriller movie or anything like that where someone was put down by chloroform, but it doesn't work quite that way. I know it's disappointing. It's funny when it happens sometimes, but it is what it is. And then we have tetrachloromethane, which is actually used as an industrial solvent. So they have some uses. And so we're not going to have time to get to our sulfur groups, unfortunately, today, but we will certainly get to them after our exam is completed. So I'm going to stop recording.